I want to talk to you about some work that we are doing in automating bone age assessment from pediatric X-rays. This is work done in collaboration with a lot of folks. I'm going to put up my acknowledgements right away. So that is Dr. Anuradha Khadilkar. She is at the HCJMRI, the Jahangir Medical Research Institute in Pune. That's Dr. Vaman Khadilkar. This work is done also in collaboration with Dr. Lars Savndal, and that's me. There's a number of other doctors who've contributed to the bone age ratings. That is Mukta Saxena, who was a postdoc until recently in our lab on this work. That is Rashmi Chapke. She was a BSMS student at IISER Pune, and she wrote a master's thesis on this topic. A large part of what I'm going to talk, this work is supported by HMRI, IISER Pune, the Karolinska Institute, and we've got funding from the Department of Biotechnology, Government of India. So a lot of what I'm going to talk about is going to be Rashmi's work in her thesis and some of the work that we are jointly doing. That is her thesis citation. It's actually available at the dissertations server on IISER Pune. She just graduated a couple of months ago, weeks. This is a new paper that is in preparation. I'm going to show you some of the results that are fresh out of the oven, which have not yet been submitted. So this is very fresh work. Most likely this paper is going to be submitted very soon. As I mentioned, this is part of an Indus-Swedish collaborative grant by the DBT, given to us by the DBT, and those are the PIs with us as co-PI. I also want to acknowledge the Param Brahma supercomputing facility, which provides us with GPUs without which this would be very difficult to do. So let's talk about bone age predictions, what they are and how we want to do it, and where does machine learning fit into all of this. Okay, there are two dominant methods from in the clinical literature. One of these is called the Gulick-Pyle method, and the other is called the Tanner-Whitehouse method. I'm not going to focus so much on the Tanner-Whitehouse, so we can discuss this offline if anyone's interested. I'm going to talk a lot more about Gulick-Pyle. So all of the work that we're going to describe in this talk is to do with the Gulick-Pyle method and its extensions of it that we are developing. So the standard Gulick-Pyle method takes a standard set of X-rays. It's an atlas of X-rays of children whose hands have been X-rayed at various ages. And the job of clinician, when you're looking to ask for a new X-ray, what is the likely age of this child whose X-ray is being presented to you, is to compare it against the library of images in the Gulick-Pyle atlas. And whichever match is the best, that match stands in for the age of that child. So as a machine learning problem, this is an interesting problem for the reason that we have a bank of images standardized, and you'd like to be able to ask, if you present a new image, which of the images in the bank is most likely the best match, and you present the age that corresponds to this match. As it turns out, the problem is not quite so simple. And my talk is going to be why it's not as simple as this. Okay, so I like to mention early enough that the Gulick-Pyle method is by far in the clinic the most dominant method. Even though Tanner-Whitehouse methods are a more recent, perhaps one might say a more advanced form of bone aging, the largest number of clinicians use the Gulick-Pyle. So the Gulick-Pyle is essentially very important to us because you'd like to be able to do something you'd like to be able to say something to the physician who is actually trained on a Gulick-Pyle method. Okay, all right. So I'm just putting up this image to give you a sense of what the X-ray looks like in the hand. I'm sure you've seen this kind of an X-ray several times before. I want to lay out some terminology. So these bones in the fingers, those are the phalanges. The metacarpals are the bones in the upper part of your palm. The carpals are the bones, the roundish bones that sit right around your wrist. The radius and ulna are the bones of the arm. Okay, so all of these bones, and in particular what are known as the epiphyses. The epiphyses are a developing piece of tissue at the ends of the bones. Those are very interesting to clinicians in order to be able to tell what the developmental stage of that hand is. In a child, the carpals, for example, are very immature. You'd see very little development of the carpals. In the older child, the carpals are very, very mature. So this picture probably is of an older child. Okay, so why do we want to do what we want to do, and how should we formulate the problem? The bone age that you want to predict, I mean, it stands to reason that you would like to be able to do this in a relatively, in a machine learning sense, in a relatively quick span of time, because manually, these are very difficult to carry out. You need trained specialists to be able to carry out bone aging. And so you can imagine that these things would be very hard to scale if you had to do a lot of these imagings or ratings of bone age. It's an exhausting process. The clinicians say it takes a lot out of them. So it's going to be it's going to be very hard to scale. If you had a technology solution to this, then perhaps scaling with all of the caveats of what do you do? Do you use it for diagnosis? Do you use it for prognosis? Do you use it for screening? With all of those caveats in place, I'm not addressing those questions. At least it gives us a way of deciding whether it can, if technology can be made, you might have an option of scaling the bone aging. Okay, I should say that bone aging is an extremely useful an important aspect of pediatric endocrinology. So the other thing that comes to mind is that the atlas, the Grülich-Pyle atlas, has largely been developed in one population, which is essentially a Caucasian population. And it has been, over the years, extremely difficult to translate this, this atlas to other populations. There's a lot of words. This is several decades of work. It has been extremely difficult to ask, how does this Grülich-Pyle, what's the value and what's the applicability of using the Grülich-Pyle atlas, the standard atlas, to apply it for, say, Indian children, which is what our interest is really at the end of the day. So the question that the machine learning question that would be relevant for this talk, for this audience, is, can we write down a machine learning algorithm to be able to carry this out, to be able to automate this? Those are slightly different questions, but we like to be able to address both of them. So I should say now that the RSNA, the Radiological Society of North America, has put out a pediatric bone age challenge since 2017. I'm going to read this out for you. As part of its efforts to spur the creation of artificial intelligence tools for radiology, the RSNA conducted a challenge to assess bone age from pediatric radiographs. It's a routine task that determines an important development indicator. So why is this important? This is important because the statement of the problem is very clear. The statement of the problem is that it's extremely important to be able to do this in an automated method. The RSNA actually provides a data set of about 12,000 odd images that one can use for training. So in fact, in the afternoon session, in the hands-on session, I will show you a snapshot of the RSNA data set. I've extracted a piece of it for you to work on in the tutorial session. So this is the very lovely data set, and that it's available makes it easy for us to develop algorithms without having the burden of having to do the clinical research itself. Each RSNA image is actually GP rated by 6 raters. So this is important for us. The rating is a rating of 6 raters. Why do we need this? We need this, or why is it done that way? It is done that way because matching a photograph is a very subjective exercise. So what's the gold standard that you develop over there? Well, you take one rater and ask them, one trained specialist, and you ask them to rate it. Let's say they claim that this is an image corresponding to a 120-month child. Another one might come along and say, well, you might say it's 120, but I believe it's 132 image plate, 132-month image plate that matches this closer than, and so I would rate it as 132. Well, now you've got a discrepancy between 2 raters. You've got a discrepancy between 2 raters. So you want to collect as many independent ratings as you can get, and then average those over and say, well, the consensus is the average rating on this image, right? So this is how consensus is built when there is an inter-rater variability. And for that reason, each one of these is rated by 6 raters, which is quite an intense job. But it's been done. It's been done. So every RSNA data, every RSNA image, every image in the RSNA data set has been rated, and that label is available to us. There's a training set, there is a validation set, and then there's a test set. And naturally, as in all machine learning questions, you would like to train on a training set. You would like to be able to use the validation set in order to decide when the training is when the trained model is a good model or not. And then we'd like to be able to deploy it on the, test it out on the test set in order to decide whether the generalization of your model, what the generalization error of your model is. Okay, so let me show you a little bit about the RSNA data set itself. This is the training data. It's a histogram of the training data. You got ages from very small to nearly adult. This is the number of X-rays that are available to each of them. When you, right off the bat, you notice something. You notice that a lot of the images are of between 10 to 14-year-old children. And there's very few images that are actually available at these tail ends. So this tail end is actually not so much of a problem, because the child, once it's past their puberty, the hand is relatively close to being mature. So while this is not quite, I mean, of course, you'd like to be able to have sensitivity in this region as well. There is a lot of sensitivity that goes missing because the data set has very few images in that. So that is one caveat that one has to remember in applying this in the clinic. If you had a machine learning algorithm that was trained on the RSNA data set, you would have to ask, is this really good enough to apply for very young children? That's some question. That is a question that we are working on addressing, and it's a very important question for us. So this histogram is extremely important to keep in mind. It's gender balanced, so there's not that much difference between the numbers of images that are between. So you have class balance between males and females, so you don't have to worry about that as much. So what one typically does is you build models that are not sex agnostic. So if you try to build in one model for males and one model for females, and you would say, I would suppose that I know the sex of the child, so I can use the appropriate model. Okay? That's the way we do it. There's other ways to do it in which you are sex agnostic, and then one of the ways in which you have one of the first steps is to find out what the age is, find out what the sex is, and then let your model develop, predict what the sex is, and then use an appropriate model. Either way is fine, but we are going to assume that the sex is known, so we're going to build models in that way. Okay, so we did build a model, and we built several models. When I say we, it's largely the work of Rashmi working with us, working with me. This is, for example, so I'll show you some of the results of the many models that we built. This is a ResNet for some of those of you who recognize the zoo of convolutional neural networks will recognize what the ResNet is. The ResNet is a very popular CNN. And we've used a relatively large ResNet. So ResNet 18, ResNet 50, ResNet 152 are models of successive sizes. We used a relatively large ResNet 152, ran quite a few epochs on it. And one predicts that the full hand GP prediction is actually quite nicely obtained for us. So that's the bone age, that's the ground truth, and that's the Grülich pile prediction from the full hand Grülich pile prediction, the full image predicted age. Okay? So you can see the age has a very nice tight correlation. And in fact, that's the kind of graph that we will work on in the afternoon in the session today. So the metric that's used for describing whether or not this is good enough is the absolute deviation, the mean absolute deviation, MAD. One wants to get it under about 6 months. So the average deviation in absolute terms is not more than 6 months. That's good enough for clinical practice. The MAD in this case, for this model, is slightly higher. It's about 7 months. One can work a little hard to produce models that are of slightly lower MAD, but I'll have more to say about that. MAD 7, so between 6 and 7 is reasonable in our hands. It's what works in our hands. One can try to build MADs that are slightly lower than that. State-of-the-art MADs have been reported. A lot of people, by the way, have worked on this problem. So I'm afraid I haven't shown you all of the citations to those papers that have gone before us. I'm happy to discuss it offline if anyone's interested. And typically between close to 6 months is what's reported. Between 4.5 to 6 months, MAD has been reported. The best being for about 4.5 months. But this is appropriate for us. So one can stop here and say, well, I have a machine learning model that does well in terms of the population at the population level, and I can stop. I have a model that does very well. I'm able to predict the age as against a reference standard, and I'm doing fine. Well, where do you go with this? Hey, you're done. Not quite. Well, this estimate is only valid at the population level, but is it really good at the individual level? Would you use this model for predicting bone age in individuals? Well, no, not quite. Why? Because the variance is large. The variance is substantial. So you can notice that for a child of say 100 months, you have a large spread in the predicted bone ages, right? And you'd like to be able to understand. One likes to be able to understand, well, what can explain the variance? So the real question in bone aging is not explaining the mean; it's explaining the variance. Because the variance, if you can get a handle on that is what would help us explain why for a given age, given ground truth age, you would actually get a lot of different predictions from the algorithm. Now, mind you, this is not different predictions of the same image. This is different predictions, different images, all of which the human raters have rated to be of a particular ground truth level, but the machine has decided to rate them different from the ground truth. Okay? The ones that fall on this line, there's a lot of them that fall on the line exactly. And those are great. Those are predictions that are exactly bang on. But the predictions that are off, that's the hard part. Okay? So that's the hard part in this. That's where the angels fear to tread. So let's go to that question. Okay, so after working on this problem for several years, it's been several years now, we have a number of hypotheses, and I'm going to go straight to the hypotheses that seem to be the most promising, and those are the functioning hypotheses, the actual working models in our lab. So we've written a paper in which we have claimed, this is on medRxiv for the moment, we've argued that one of the reasons for differences in bone age assessment. Now, remember that I said that there's inter-rater variability in bone age assessment. Okay, what you are trying to drill down, what we are trying to drill down into is why is there inter-rater variability? Okay, you can simply claim, and many papers exist to claim that this is the size of the variability of the inter-rater variability, and that is known for many different populations as well. But you would really like to be able to understand why is there inter-rater variability, and there's no clear, clean answer to it. There's a lot of subjectivity in it, so one has to guess at what might be leading to this variability, right, between raters. So one of the reasons for the differences BA is due to the weights that different raters place on the different regions of the hand while they're assessing. It's a subjective assessment. So imagine that you're taking a fresh X-ray and you compare it against plates. You've got a plate of a 120-year-old month child. If 132-month child, the rater is trying to, the clinician is trying to compare it to see whether it matches this one or it matches that one. And what if the rater subconsciously places emphasis on, say, the finger area or the wrist area much more than the other places? Okay, so there's a subjectivity involved in in placing weights on the different segments. I'm going to call them segments, and I'll sharpen that point a little in the next slide. Segments of the hand are differentially weighted in a subjective manner. Now, how can we hope to make this subjectivity objective? It seems entirely difficult to do. But that is one source where two raters might differ because of the subjectivity involved. So the next point is that there is another reason why you can have variability in the rating. And that comes down to the bones of, yes.
So I presume this rating is the method which is used to determine the bone age. I mean, how does the rating transforms to the age of the bone?
By rating, I mean the aging. I report what the age is. So I take an image, or the clinician takes an image, compares it against a standard atlas. And if this image in the atlas is of a certain age, that's the rating of this image. That's the age of the, it's the reference age that is being prescribed to the age that you're measuring, of the radiograph that you're measuring.
So different parts of the bone you said have different ratings.
Two different raters can give two different ratings for the same X-ray, because they might see different, they might place emphasis on different parts of the hand that they're comparing to the standard atlas.
Okay. And the plot that you obtained, the variability was from the algorithm, right? I mean,
we don't know where the variability comes. So I'll have more to say about that. So sources of this is inter-rater variability in the clinician's ratings.
Can you go to that graph again and tell me that what is that full hand GP predictions?
Right.
Sorry, I didn't.
So this,
yeah, y-axis.
This is the prediction of the bone age that comes from your algorithm, from your trained neural net.
The original. That is the.
And that's the rating in the RSNA ground truth level.
Thanks.
Okay. So I was trying to come down to creating some sort of a mental model for where the rater variability could arise from. Okay. And this is a subjective thing, remember, right? So we're trying to isolate the sources of variability that could be coming from. The other source that we think of rater variability is that there are different parts of the different bones of the hand that could be actually matured differently. So you imagine, for example, the carpals are matured faster than, say, the phalanges, and one might, the rater has a dilemma that should I place emphasis on the carpals or should I place emphasis on the phalanges? If I place emphasis on the carpals, I might rate it as 132. If I place phalanges, which are differentially matured, which are relatively retarded relative to the carpals, I might call it 120. So I have to make a choice. I make a choice. I call it 120. Okay. So the fact that you want to acknowledge the different bones of the hand could be matured differentially in the same hand would also lead to rater variability, right? So in summary, there are two sources of inter-rater differences. Focusing on different bones is a subjective judgment, and that subjective judgment may differ from people to people, and so the same image may be rated differently. There's differential bone progression. This is a well-known idea that the bones don't always uniformly progress in all persons in the same manner. So there might be individual differences in the bones themselves. Okay, those are two sources of rater variability that we can think of. And now the job is to try and cast it into some machine learning language that we can then deal with these questions. Okay, so here's what our solution to this problem is. Our solution to the problem is we claim that the hand should be segmented into three large regions. We'll call these the wrist bones, the region around the radius and the ulna, the carpals, those are the bones that sit above the radius and ulna in the wrist, and then all the other bones we'll call the short bones. The phalanges and the metacarpals, those are the short bones of the hand. We will therefore divide three segments of the hand. And what we're going to do is we're going to try and image the three segments and ask what the rating is based on the segments alone. So we are going to develop a segmental rating system. If I were to present the hand radiograph, can I segment away the carpals and ask what the carpals rate corresponding rating is, right? They're all going to be trained on ground truth. So what our expectation is that the carpals alone, or the carpal segment alone, that photograph, that segment ought to be able to tell us what the age of the hand is. So you will get an independent rating for each of the 3 segments of the hand. And let's ask how that does. So ideally, if there's a differential maturity of the hand, you'll be able to pick it out in the differential ratings of the 3 segments. That's the hope. So there's a bit of a problem there, though. We want to develop a bone aging system that provides segmental Grulich pile in the sense that I just described. But then if you wanted to ask for an overall age, which is kind of the clinical question anyway, well, I don't care how the hand is matured. Tell me one answer for what you think the age of this child is. Well, then the question becomes, how should the segments now be combined into an individual age score? So you've got reduction down to segments, but then you have to aggregate back to the macroscopic level of what's the overall age. Okay? So those are the questions that we're going to have to address. Okay, so I'm going to walk you through. So we developed a method in which we actually get segmental ratings. I'll walk you through what this method is. It's a very straightforward method of using of segmenting the hand. So first we want to take a radiograph of the full hand, and you want to extract the relative segments of the bones, right? So a training set of 160 samples and a validation of 40 samples, roughly distributed, was taken by Rashmi, again, relatively balanced in gender. And she decided to annotate every section painstakingly by hand. Those are the carpals, those are radius ulna. She marked digitally all of the different sections, phalanges and metacarpals. Together, these are short bones. So you've got 1, 2, and 3 segments of the bones. She painstakingly painted them. And now you've got the original hand, you've got the mask corresponding to one of the segments. You train a network to recover from a naive photograph what the right segments are. I'm going to show you what that result is. It's the model is a segmentation model. It's a UNet, which is very widely used for segmentation problems. If anyone's interested, we can discuss this later. And there's some training losses, some validation losses. I just want to flash the slide to show you that what you're looking for is a dice score in describing whether or not you've got a good segment. Does it overlap well with what you expect the region to be? And those all turn out to be very good. Again, that slide I just flashed for you in order for you to pick it up if you want to discuss it later. And here's what the outcome is. If a full hand is presented, the 3 segments are, all of these are segmented away. You've got your bones of the hand, you've got your carpals, you've got your metacarpals, you've got your phalanges. So she's gotten very good at, the coach have gotten very good at taking a full hand radiograph and segmenting it into the 3 segments that we want clinically. Okay, so if you're convinced of that, now we can proceed further and ask, if I had taken the full hand image and compared it against the ground truth, well, I get this line. I've shown you this before a couple of slides ago. If I took only the corresponding wrists and trained a network to predict the bone age from just the wrist segment, how well would I do? Well, you actually do very well. So in other words, this is proof of concept that whether you use a segment to produce bone age or whether you use the entire hand to produce a prediction for bone age, you're actually doing very well at the population level. Okay, so moving forward, how's this useful to us? Okay, well, the first thing it tells us is if I take one hand image and I ask for a prediction of the wrist and a prediction of the full hand and a prediction of the average between these, take this one for example, you actually get a difference between the 3. So the full hand prediction is orange. That is different from a wrist prediction. It's the same hand, just a segment of that same hand. And then if you average the 2, well, you get something in between, right? So this shows us the differential maturity is evident even at this level of aging. So of looking at of training. So in the CNN predictions, the neural networks trained for the wrist, the neural networks trained for the full hand are actually going to get slightly different answers. Okay.
When you say wrist, you mean the radius part?
Wrist, yeah, radius and ulnar part.
Okay.
I think that's what it is. Yeah. Okay, so let's look deeper into the problem. Okay, is bone aging a classification problem or is it a regression problem? Right? For all the machine learning aficionados, what do you think it is? Well, if you look at the Grolic-Pyle method, it's a classification problem, right? It's a classification problem. Why? Because you have a certain number of classes. Those are the Atlas libraries, and you want to take a naive photograph and say, tell me which class does it belong to? What's the highest probability of belonging to class 120? Okay, that's what the question is, right? Turns out that's not what you do. It is a regression problem, and here's why it's a regression problem. Due to inter-rater variability, you're never going to supply, the ground truth is never going to be 120. It's going to be between 120 and 132 because multiple raters have rated it. There's going to be a lot of photographs that are 126. 126 is not a standard Grolic-Pyle plate, right? So what do? Well, should you keep 126 or should you switch to 120? Well, you started at 120 and 132, but you had an average rating of 126. So invariably, you're getting a number that is in between plates. And if you're getting a number in between plates, then you treat bone age assessment as a regression problem. You say, well, here I'm going to present you this this plate. Give me a number what you think is appropriate for the age. I don't care whether this is aligned to the Grolic-Pyle Atlas plates, the reference plates or not. So it turns out that this is a regression problem. The regression, so it's a very interesting sequence of events that led to it being a regression problem. Classically, it is supposed to be a classification problem. You do multiple ratings, which turns it into a regression problem. Okay, so that's interesting in its own right. Okay, so well, now we are going to treat bone age assessment as have all of to the best of our knowledge, all of the methods that have gone previously have treated it as a regression problem. So also we are treating it as a regression problem. If you treat it as a regression problem, one steps back to ask this number that you get at the end of the day, the prediction that you get, what does it mean? What are you predicting? Are you predicting which plate is matched? Well, if it's a Grolic-Pyle system, I'm supposed to tell you which plate is matched, right? But you're not doing that. You're giving it numbers that the human raters have produced. Each one of them has been matching it to a plate. So it's a discrete problem at the level of a single rater. But when you combine multiple raters, it becomes a continuous problem. If it's a continuum problem, what you're actually getting is trying to match the human rating, not the Grolic-Pyle Atlas rating. This is a very important point. It takes quite a while to reach to this conclusion. If you're matching, you're trying to get closer and closer to what multiple humans would say this match is. Multiple humans, not a single human, right? So you're trying to approximate what a clinical rating would be if this image had been showed to multiple specialists. That's what you're after, okay? This means that the bone aging system has rater variability built right into it, in the very process of what you expect and how you are going about solving this process. Inter-rater variability is built into the system, right? So that any expectation that the trained networks can do better than humans is out the door. It's just kind of counterintuitive if you think about it, right? A lot of us would like to say, well, you know, there's so much data variability. Can we use a machine learning network to get the right answer, whatever the right answer is? I don't care that, you know, that there is just so much human variability that's kicking in. Well, in this system, in this setting, you're not actually throwing out the data variability, you're building it in. So you are not going to get an answer that is somehow magically better than everyone else, right? It is the consensus rating. And what you're after is a clinical consensus rating. That's another of the points that you know, that was a revelation to us when we thought about it, because I don't think that's been discussed previously in any of the papers we've read. So we're writing a We're writing an article on it. Okay, well, you could ask another question. If you train your networks, train them to death, train them exhaustively, what shouldn't you be able to get better and better and better and better and better? What do you think the answer is? The answer is no. You can't get better and better. There is a fundamental limit, we think, that you cannot get better and better at the system, and it is due to inter-rater variability. That inter-rater variability is a source of randomness that gets built into the system. So I can show you a back of the envelope calculation that claims that the lower, no matter how well you train, you could use fancy networks, you could use image nets, and you could use res nets, and you could do ResNet 152, and then you could go to dense net. We've done all of that. And we use really, really fancy models, very, very large models, and so on. It turns out that there is a sort of limit beyond which you cannot lower the MAD, right? And if anyone's interested in this back of the envelope calculation, I can show you why this is. But essentially, we think it comes down to you cannot disambiguate between two different classes to precision. So you're going to have to allow for something that is within 1/2 interclass distance to be equivalent. And if you do that, you actually take all of the interclass distances, take an average of it, and it tells you that you cannot have any lower than 3.8. The MAD cannot be lower than about 4 months, 3.8 for girls and 4.2 for boys. And this is based on a quick and dirty calculation that you can do of the Rolic Pile Atlas itself. So the summary of it is that the rough calculation shows that the minimum MAD that you can expect from training networks exhaustively is limited to about 4 months. You should not expect to do any better than that. Why? Again, because data variability is built into the system. Okay, so a purely computational solution has its limits, namely 4 months. We need another strategy. What are we after? We are after being able to describe for individuals what is the likely prediction, what's the best prediction you can make for individuals, not for the population itself. Okay, so if you're limited by your MAD to be about 4 months on a population scale, well, how can you do better at an individual scale? At an individual level, you need to be able to do better. How do you do that? What do you try? Okay, so back to the drawing board. We need to understand the source of data variability. I just described to you a couple of slides ago. The raters could be differentially weighting different bones. So this is one direction we are approaching to. If you could understand how are different raters rating different bones, then that we could pursue that line of reasoning and say, well, the carpals were important below puberty, and above the ages of puberty, the carpals are less important. And so we've written papers. We are writing papers on those lines as well. And then bone segments could cause differential maturity in the hand might mean that, one segment of the hand is advanced relative to another segment of the hand. Okay? And now that we have a facility for rating segments individually rather than the full hand is a composite, the full hand is likely to be a composite in some sense, which you've not clarified yet. But we are looking for segmental ratings and asking what can we do with segmental ratings in order to be able to do better than just looking at the full hand in total. Okay. So about 4 months, yeah. Right. So I can get into that. If you think about let's say you have a rating that you want to place between 130, 120 and 132. Then, let's say the rating that a human rater would put would be somewhere here. Now you have to decide whether you want to club it with this or whether you want to club it with this, right? So also on the other side, right? So in other words, all of this region is actually sort of equivalent, right? So if you tabulate on average, what's this distance? The average interclass distance, that turns out to be about 4 months. That's my estimate of what a minimum could be. because, yeah. For any model. Well, I don't want to generalize because it has to be very model specific and question specific. In this case, I think this is a reasonable limit and most models have come close to this, but they've not reached this. So we think it's a reasonable limit. Okay, so my strategy for looking at the hand rating is to look at segmental ratings, but I have this question of, what shall I do with the segmental ratings? Even though I can get segmental ratings, I need to be able to put it all together. So a segmental understanding of bone age is key to resolving these questions further. How should we proceed? First, we need to establish that segmental ratings actually correlate well with the RSNA ratings. So this is, I showed this slide a little bit earlier, only for the wrist, but now you can see that, the full hand, this is boys, this is girls, full hand radius ulna or short bones or carpals, they have very high R squared compared to the ground truth. So segmental ratings by themselves give you a good sense of the age on their own. Okay, so the reason I'm saying this is because this allows me to treat them as independent assessments of bone age. Okay, which is by construction, by design. I want to construct segments and I want to be able to get the bone age based only on the segments, right? So we don't think this breaches the general Grulich-Pyle paradigm in a sense, because all it says is even I'm matching plates to the relative to the template, but I'm only looking on a portion of it. In a sense, it's an attention mechanism of sorts. I attend only to a portion of the plate to make the decision, which, taken it to its limit, is to blank out everything else, focus only on the region of interest. Okay, so once we establish that, we can get segmental ratings. They do well. So the next thing I want to introduce is something called the concordance curve. The concordance curve, so I should say that, segmental ratings, we've been able to get segmental ratings. It's a work in progress, how we combine segmental ratings in order to be able to get bone age, a total bone age. And the answer is a little bit complicated. So, and the story is not quite as mature as I'd like it to be before I'm confident in describing it to you. So I'm going to leave it at that. But suffice it to say that different populations actually have different weights of the segments attached to them. So if we can work out the right segmental weights, you'd be able to get the right bone aging formula for how to combine weights, segmental ratings towards a total hand rating. Again, this is all referenced with respect to the RSNA. I will tell you one slide later that we're redoing all of this work. Not we, our colleagues are doing all of this work for rating segmentally Indian radiographs. So there's several thousand Indian radiographs that are available with our colleagues, and they're painstakingly rating with Grulich-Pyle not only the full X-ray but also segmental ratings. So we in a few months, we've already started that work. In a few months, we will have validations, I hope, on Indian radiographs for segmental ratings. Okay, let me just show you something very cool that I think, which if anyone want to pick up on this and discuss with me, I'd love to. This is something we'd introduced called the concordance curve. So we are describing all plates, let's say, all of the plates that have been rated to be identically 120. You've got different plates in the data set, or let's pick out all of the plates that are 120 months. Okay. If I ask, what are the network predictions on all the plates on which the humans do not have any difference of opinion? So all of them are rated to be 120. Right? If the human ratings do not have any variance, does the network show variance in that? It turns out that it does. What is the distribution of network ratings on a subset where all of the human raters have agreed it's 120 months? One curve for 120, the other for 132. It turns out that the distribution is a Gaussian, nearly a Gaussian distribution, and the mean is close to being about 120. So it seems like the network We'll be doing one or two things. Either the network knows that it's 120 up to a distribution that it cannot further qualify. So it's sort of sampling from a distribution, sampling various predictions from a distribution centered on 120. Or it could be something more deep. It could be that the network is actually picking out finer differences. It knows to distinguish 124-month image from 120 image based on certain calculations that it's doing in the black box that it is. And the humans have all decided it's 120 unambiguously because they need to quantize between 120 and 132 versus 108. So they've decided to 0 and 120, but the network knows that it's slightly different. Okay, which of the two possibilities is it? This is a very intriguing line of analysis, and we are currently working on exploiting this for even higher resolution bone age assessment. Again, that's a story for later. This is currently being developed. Yes.
So what are the two curves for? So one is both are cumulative distribution functions.
These are empirical cumulative distribution curves that have been fit by a Gaussian distribution. This line corresponds to the 120 plates. This one, for comparison, is all plates at 132 by human rating. All of these, everything on this curve has been rated to be 132 months by human raters. And you get a nice distribution around it. So this is something that we are working on, and hopefully the next time I talk about this, I'll have a better understanding of what exactly does this mean? Can we break this black box to figure this out? Okay, so I'm very close to near the end. I want to show you that we built an app, Rashmi's put together an app based on our codes. It's a Streamlit app that actually does this on the very nicely for us through some interface. It's a web-based interface. You simply plug in an X-ray of the hand. It segments out the segments we are interested in, and it gives you an automatic rating for it. So that's just to show you a little example of how this could be useful in practice if we need it to be deployed in some manner. Okay? And I'm going to give you a slide of the future work that we're working on. I'm going to show you. We believe that it's important to be explicit about segment-wise age rating. And at the same time, we also want to be able to combine those independent segment-wise age ratings into an overall assessment. Finally, we want to use the networks that we built on the RSNA dataset, which is a widely applicable dataset because it's sort of the go-to set for an international population. But we want to be able to use, say, techniques from domain transfer learning to specialize what that network would do, or how would you translate it into an Indian populations. As I said before, collaborators at HCJMRI are painstakingly rating manually thousands of X-rays, and this has been a project that's been going on for several years. All the people that you saw on that slide have been involved in this one way or the other in the acknowledgement slide. We have begun testing the trained networks on Indian data and developing metrics to translate the segment methods so that these networks are then applicable not only to RSNA, but with appropriate modifications to Indian children as well. So that's our goal. This is where we are. Thank you for listening.
Thank you. Very interesting talk, Pranay, and he'll explore some more of this in the hands-on, I guess. Any questions? There was somebody, but yeah, go on.
Okay, so my question is, sir, when you combine the segmental data, so do you have have you figured out some combinations of segmental data like metacarpals and wrist, and then take the scores, or you just put one, the full hand, and then take the score and separately the segmented score, or
Right.
like?
So excellent question. That's one of the key questions that we're working on right now. So we've tried to answer this question both clinically, and now what we're working on is to try and ask this question in a machine learning sense. Those are two slightly different questions. One question is, if you had segmental ratings, then what's the best way to combine segmental ratings? I can give you an example. I mean, for example, once the hand matures, so beyond puberty, the carpals are no longer interested. A clinician, they mature to the maximum value, so they're less weighted in terms of giving a combined score. So we have worked out, and that paper that's on medRxiv actually tells us what these weightages are. They're not uniform. They're not simply taking an overall average of all of the segments. What we'd like to be able to do is to show whether we would like to ask whether a same weighting would work if you would go to naively train neural networks to get the right full hand rating, or would you get a different answer? That'd be an interesting question. We've not yet gotten to that.
Yes. So is this like going to be the ranking based combination, or you'll train with the images, like both the segments together or combination of segments together?
It'll be training based.
Be training based.
Yeah.
Okay. Thank you.
Sir, I have a question here. With the help of this model that we have developed and the type of the work, so suppose that we found some bone. Okay, so will we be able to predict the age of that bone?
A single bone, or the entire hand?
The entire hand.
Yes, that's the goal.
You found a bone, you are saying you
Like
found it in the ground or
Oh,
something?
you found only a bone.
No, sir, like suppose that we have found some skeleton,
Right.
and that skeleton is having the hands also. So will we be able to predict the age of that skeleton with the type of the model that we are building?
Well, yes, if you had an X-ray of a skeleton, then I think you should be able to, because it's based on the maturity, on the bone structures and their maturity. As the child's hand ages, the maturity of the bones themselves become different. So depending on what the bones look like, you should be able to age it.
So for example, if you have some archaeological bone or something and you want to determine the age of the fossil or something.
So in principle, yes, because you will see bone structures that would be different in a child's hand that is closer to an adult than you would see in a child's hand. The size of the bones would be different too, but you would also, a child's hand is smaller, right? So the size of the bones will be smaller, but also the epiphyses carry a lot of information.
So will it be like general for different ethnicities? Because if we were to do this study for a fossil which was which spans over like lot of time and also ethnicity, will it be?
To the extent that biology hasn't changed presumably that much between, say, something that existed 1,000 years ago and what would be now, then I mean, I'm not so sure what secular trends might have existed in aging between, say, a couple of 100 years ago and now. That's a question you would have to ask somebody who's a pediatric specialist. For example, the child's hand might be more mature at, say, age 8 than, and for another population or another time period, it might be that level of maturity only exists at age 10. So if those kinds of secular trends are available, then they would have to be taken into account. But in principle, you'd be able to do the sort of Brolik pile assessment that I described for any set of bone structures that are available to you.
There was a guy back there. Do you have a follow-up? Yes, please.
So like, can we say that is it, if you compare it with the carbon dating, is it going to be better than that or like comparable?
I'm more interested in live children.
Pardon, sir?
I'm more interested in live children because bone aging is a very important indicator of a child's developmental status. If there's a lot of lag between the chronological age of a child and the developmental age of a child, well, then that's the point of intervention. That's when you need to intervene in order to get the child's growth right. Okay? So I should have said this earlier, but aging a child is extremely important to know whether they're developing to their full optimal maturity or not, whether they're likely. It's a projective assessment. You want to know children should grow well to what their optimal growth potential is. That's really what the question we are after is.
Just to add, carbon dating will tell you how old that bone is in terms of 1,000 years, 2,000 years. It won't tell you how old the child was when he died. Continue.
Sir, so you have said that you have measured the agreement between the raters. So I want to know how you measured that agreement.
Measure the agreement between raters.
Yeah.
I mean, so clinically, the way it is done, I haven't done it. I mean, in the RSNA data set, for example,
Yeah.
6 different raters, clinically trained specialists,
Mm-hmm.
know how to read bone age.
Mm-hmm.
They've been asked to give independent assessments.
Mm-hmm.
The ratings are averaged between the 6 of them.
Okay. So means how did you find means in your thing? So you use some kappa statistics or what did you use to means how did you find that those are the agreeing to each other or not?
No, they don't have to agree with each other. If I got your question correctly, the clinical raters all
Mhm.
independently give their own ratings,
Okay.
right? I do not discriminate between them who is right or wrong. We say all of them are right, and we take an average and say this is the consensus rating. If 2 raters rate 120 months, you take one X-ray and one rater says this is 120 months. Another rater says, no, I think it's 132 months. It's the next plate. Well, then you say, well, 120 a month, 132, let's call this a 126 month child.
Okay. So you don't have a gold standard for
That is the gold standard.
comparing.
That is the gold standard. The consensus rating is the gold standard.
But gold standard is still varying, right?
No, I'd like to make this point very clear. This is a clinical assessment,
Uh-huh.
right? Do you know a gold standard for Parkinson's disease?
No, sorry.
What do you do then? No diagnosis possible? Wait for a gold standard, you won't get any diagnosis. So the point that I'm making is there are a lot of clinical decisions. These are called clinical decisions because they're dependent on judgments made in the clinic by trained specialists.
Hmm.
So I know people like to talk in terms of gold standards, but gold standards only exist in certain specific circumstances. The gold standard is the consensus rating. I mean, this is why we're working so hard for it. Right?
But somewhere you said that your model is able to pick the value between 2 values. So you are saying that that model is able to pick the features of
It could be.
okay,
I don't know that
finer features of the image.
that's a fantasy. We don't know that that is true until somebody teaches me a theory of deep learning, a mathematical theory of deep learning. That's the holy grail. I don't know.
But what I means, it's my perspective. What I think, if that model is trained on those consensus, so that theory might not be correct.
Okay, that could be. I mean, it could be that there's an ambiguity.
Yeah,
There's a randomness that's attached
exactly.
because the interdata variability is built into it.
Exactly.
Model has no choice but to report
Exactly.
a distribution. That's one possibility.
Yeah.
But is it an unbiased? I mean, does the model just say, well, I cannot distinguish between 120 and 130, so let's just pick out 125.
Yeah.
No, that could be the case. I want.
Yeah. So maybe we should avoid over interpreting
Possibly.
or making these guesses.
One more question and then we'll take one.
Yeah, so I would like to add about ask question about something that I have in my mind, that you have 6 rating, which is gold standard because they come from clinicians.
It's a consensus rating.
Consensus
Let's not
rating.
use the word gold standard.
Yeah, as in it's a clinician
It's a groundwork
word.
label.
Yeah.
Yeah.
So what I'm saying is is there one of the thing one can do is find out if there is a possibility of human error by comparing the two and
But we know
removing
there is
few
human
of
error.
them, and maybe accuracy will increase because of that.
Let me back up. I think I tried to make this point clear earlier. You're not trying to disambiguate between raters. You're not trying to disambiguate between raters. You accept what the raters have clinically judged it to be. You're trying to come close to what the consensus rating is, which is an average of multiple trained specialists.
Okay, with that, let's thank Pranay again,
Thank you.
and we'll break for lunch.